Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be learning all about the electronic expansion valve. We'll look at how they work, where to locate them, and why you should use them. Today's video is brought to you by our partners over at Danfoss who have kindly sponsored this video. Danfoss is committed to providing the very best solutions for a wide range of applications, including chillers, cold rooms, and heat pumps. These solutions include their series of high-quality electronic expansion valves, which are approved for use with all common refrigerants as well as a wide range of capacities and pressure ranges. The compact and durable design make them easy to install while enabling significant energy and cost savings. You can check out their entire range of electronic expansion valves by following the link in the video description below. Electronic expansion valves are used in refrigeration systems to precisely control the flow of refrigerant into the evaporator. You can find these on everything including VRF units, inverter mini splits, heat pumps, chillers, AHU coils, etc. Now, we've previously covered how thermal expansion valves work. These are very common in refrigeration systems, but they are nowhere near as efficient or precise as an electronic expansion valve. If you haven't watched the video on how these work, then I highly recommend you do so. Links are in the video description below. Electronic expansion valves are an evolution on the thermal expansion valve. They are much more sophisticated and allow the refrigeration system to operate much more accurately and efficiently. You'll usually see the electronic expansion valves listed with the acronym of either EEV or an EXV. They both mean the same thing, it just varies by manufacturer. There are many benefits to using an electronic expansion valve, and I've listed some of the main points on screen now. The focus though is usually that by using an electronic expansion valve, you're going to reduce the energy consumption of the refrigeration system as well as gaining much better performance. What do electronic expansion valves look like? There are many different designs for an electronic expansion valve, and I've put a few examples on screen now so you can see how their appearance varies. The difference in design depends on the type of system, the refrigerant used, and the pressure it's working with. As you can imagine, a small split AC unit isn't going to need the same valve as a high pressure industrial application, so the design is going to vary. Although, the basic working principle is essentially the same. Main parts of the electronic expansion valve. As we just saw, there are many different designs for electronic expansion valves, but we're going to focus on a simplified design to help build your base knowledge. This design uses a permanent magnet stepper motor. At the head of the valve, we have the stepper motor body, which contains the copper coils. These are used to generate an electromagnetic field, which will be used to control the valve's position. Sitting concentrically within the main body of the stepper motor is a permanent magnet. This permanent magnet is affected by the electromagnetic field of the coils, and the change in polarity of the electromagnetic field will cause the permanent magnet to rotate. Attached to the permanent magnet there's a shaft. Now, some designs will use a gear assembly between the motor and the shaft, but as we're only looking at a simplified example, we're going to stick to a directly coupled shaft. On the shaft is a thread. This thread sits within a holder which is attached to the valve body. At the end of the shaft is a valve needle. Then we have the valve seat, which the needle moves into and out of to close and open the valve and control the flow of refrigerant. We'll also have some temperature and pressure sensors to take measurements of the refrigerant in order to calculate the superheat. These will be connected to the controller. The controller is then connected to the stepper motor and will tell it how much to open or close to maintain the correct superheat. So how does an electronic expansion valve work? If we have a look at a typical refrigeration system, you can see the main parts being the evaporator, the compressor, the condenser, and the expansion valve. The evaporator collects all the unwanted heat from the building and transfers this into the refrigerant, which causes the refrigerant to boil and evaporate. The compressor then sucks in this evaporated refrigerant, which is a low pressure, low temperature, and slightly superheated vapor. It then compresses this into a smaller volume, which causes it to be a high pressure, high temperature, superheated vapor. The refrigerant then moves to the condenser, where the unwanted heat is pulled out of the refrigerant and rejected into the atmosphere. This causes the refrigerant to condense into a liquid, so when it leaves the condenser, it will be a high pressure, medium temperature, saturated liquid. It then passes down into the expansion valve. The expansion valve causes a pressure difference between the condenser and the evaporator. It holds back the high pressure liquid refrigerant and decides how much to let through into the evaporator. As the high pressure liquid refrigerant bursts through the small gap between the valve seat and the needle, it drops in pressure. This will result in some of the refrigerant vaporizing and the rest will continue through as a liquid. If you want to visualize this, it's similar to a water bottle spray nozzle. As you pull the trigger, the high pressure liquid is forced through a small orifice into a much lower pressure atmosphere, which causes the water to become part liquid and part vapor. This mixture of liquid vapor refrigerant is sprayed into the evaporator where it will absorb heat from the air or water which surrounds the outside of the pipe which forms the evaporator coil. In this case, we have a fan which is blowing air across the evaporator coil. As the refrigerant passes through the evaporator coil, it is exposed to thermal energy which will cause it to undergo a complete phase change from a liquid to a saturated vapor, still at a low pressure and temperature. During this change, there will be little to no temperature change because of the latent heat, and instead it will increase in entropy and enthalpy. As thermal energy is still being applied to the vapor towards the exit of the evaporator, there is no liquid left over to change into a gas form, so the refrigerant will instead start to increase in temperature and become superheated. After the evaporator, we'll find a pressure transducer and a temperature sensor which constantly take measurements and sends this data to the controller. Not all electronic expansion valves will use this method. It really depends on the manufacturer and the system. Some simple ones will use a single thermistor at the evaporator outlet. Some will use two thermistors, one at the inlet and another one at the outlet, and then use a temperature differential as the superheat. But we're going to focus on the pressure and temperature method in this example as it's a very reliable method and one you'll likely come across in the real world. The pressure is measured and converted by the controller, using stored data for the refrigerant being used in the system to find the saturation temperature. This is then compared to the actual temperature measurement. The difference between the two is the operating superheat. The controller then decides whether the expansion valve should open to let more refrigerant into the evaporator or close to reduce the amount entering. Once decided, the controller then sends electrical signals to the expansion valve stepper motor to energize the coils and create an electromagnetic field and vary its polarity. This forces the permanent magnet to rotate clockwise or counterclockwise depending on the polarity generated. Each time a signal is sent, the permanent magnet will rotate a fraction of a revolution to provide very accurate adjustments to the superheat. The shaft, which is connected to the permanent magnet, will also rotate, and as it does so, the threaded section inside the holder will cause the assembly to be pulled down. As the assembly is pulled down, it will cause the valve needle to reach the seat, reducing the gap between and restricting the flow of refrigerant. When the signal is sent to open the valve, the assembly will rotate in the opposite direction and the threaded section pulls the assembly up. This opens the valve and moves the needle away from the seat, allowing more refrigerant to flow. The controller is constantly taking pressure and temperature measurements and sending signals to adjust the valve position to suit the current load. When the cooling load increases, the refrigerant within the evaporator is going to boil off much quicker and the suction line pressure and temperature will increase. The expansion valve senses this and opens to allow more refrigerant in. When the cooling load decreases, the refrigerant will boil off more slowly and the suction line pressure and temperature decreases. The expansion valve will then begin to close to allow less refrigerant into the evaporator and maintain the correct superheat. Just before we go, I want to give one last shout out to our partners over at Danfoss and remind you to check out their electronic expansion valves by following the link in the video description below. Okay guys, that's it for this video. Thank you very much for watching. I hope you've enjoyed this and it's helped you. If so, please don't forget to like, subscribe and share. And if you have any questions, leave them in the comments section below. Also, don't forget to follow us on Facebook, Twitter, Instagram, Google+, and check out our website, theengineeringmindset.com. Once again, thanks for watching.